Okay, so let's get started. I'm quickly going to switch. So, do you all have your keycard installed? Do you have your keycard installed? Because I would prefer if you
Please, what is
can.
KiCad?
Yes, or any other software that you want to be using, but I'll be using KeyCard. So if you have your KeyCard installed, let's rock. So we would be using KeyCard for this work, and so I'm going to start it. Let me share the screen. All right, so launching my KeyCard. Can you see my screen?
Yes, please.
All right. So in your keycard, create a new project. So go to File menu, create new project, and navigate to wherever you want to save your projects. I'm going to save it in Let Routes, key uh, Let Route Uno. Okay. All right. So give the project name. Let's call it Let's Route Uno. Please, if you text and the message is for me, I may not be able to see, right? So I will respond to it when I check the tube. Okay, thank you. All right. So anytime you create a keycard project or you open KeyCard, you are going to see this particular window here. This is like the main program manager for KeyCard. Okay, and all these things you are seeing here are other programs that integrate with KeyCard. So KeyCard is basically a collection of other programs. So for instance, the schematic editor, KeyCard uses a program called eSchema, okay, and the PCB editor and all that. So all these are programs that you integrate. So this particular platform or this particular application, please let's turn off our mics. Thank you. This particular This particular program or the first UI that you are seeing is where you can launch all other integrated programs. Okay. Now, we would be dealing with the schematic editor in the meantime. So, open your schematic editor. When you open it, please let's turn off our microphones. Thank you. Let's turn off our microphones. Thank you. Please let's turn off our microphones. This is so not cool. Yes, I can, except that I will disrupt what I'm doing. If people could just turn off their microphones, that will solve everything. My machine is already on its high performance here. So doing any other thing tends to freeze the whole thing. Please just turn off your microphones. Thank you. All right. So we'll be using for I think in today's sessions we'll be dealing mostly with this what do you call it, the schematic editor. Okay, so quickly let's do some configurations. We are going to set up this UI that you are seeing here, the design block. And to do that, go to this particular icon, settings for paper size and title block. Sorry, we call it a title block. Okay, so I don't have any previous sheets. I'm just going to click on this to set the date. Let's call this version 1. Yeah, I'm listening.
Yes, please. Do you have this software you can run on our system? But I don't have the setup for this particular one.
Please, you may have to download that later. Okay, just follow through. I will upload the video right after this session, then you can probably follow through. Okay. But keycard.com, that's where you download the software. Okay. All right. So let's call this let's route Uno. Let's route Uno. Okay. And the company, let's call this company Tech Foundation. Tech Foundation Africa. Yeah, you can actually go ahead and fill this other stuff. Now, when you update, this information goes in here. Okay, so any other thing that you put in there should probably just show here. Now, let's go back to it. You can also configure your paper size. Currently, you can say that I'm using the A4 and the orientation is landscape. You can actually set your own custom size if you need something smaller or much bigger, or you can use the predefined sizes. Okay, all right. Now, what I intend to do in this training is to show you how I design hardware, okay, intuitively. So basically, looking at this blank screen, there is nothing much to do. But everything that we have to do has to come from here, your mind. That means, first of all, you should know what you want to do and how to do it. Okay. Now, one last thing that I'll talk about the settings is the grade. Okay. If you look on it, you can see that. I don't know if you can see it clearly. I can see some dots. Okay. You can see some dots. To configure for yours, right click on this particular icon here, go to grade properties, and over here you can actually set it. Okay. Now, usually when you are doing schematic capture, I recommend using mils. Mils is a thousandth of an inch. Okay. I recommend using mils. However, you can also choose millimeter or inches, but I'll recommend using mils. Now, when you select the mils, make sure that your current grade is having a spacing or an interval of 50 mils. If you change this to anything, you will have issues with connectivity. Okay, your connections may not snap well. Now, if you're using Altium, I think Altium the default is about 100 mils. So take note of this. Okay, if you're using KeyCard, make sure this is on 50 mils and don't change anything else in your grid setting. If you do, you are going to probably cry before you get this thing right. So please don't do that. Make sure you have 50 mils and then everything is good to go. All right. So now we have our platform, our schematic set ready for capturing. However, before we can capture, like I said, we need to know what we want to capture. So in a brief moment, let's switch off from KeyCard and learn some fundamentals before we come back. Now, I know this is probably going to bore the senior men, but please, just for the sake of the beginners, allow us to do this, okay? All right, thank you. So I'm quickly going to switch to a presentation mode and bring up a presentation that I have prepared for this program. Please, if you have any questions, there will be time for that. So just write it down somewhere, okay? Thank you. But before, as I'm opening my files, you could probably ask a question if you have it. All right, go ahead. Your line, I lost you. How do I see what? You should come again.
How do you see your file in the systematic editor after saving it?
How do I what save?
See your file in the
So
systematic
when you create a project, okay, when you create a project, you are allowed to choose the path for your project. Now, in case you didn't set the path yourself, then the default should be in your document folder. You should probably see KeyCard. I think if you go there, you should see yes. Unless you probably uh, set your own path or something. Okay, you're welcome. Please, I'm still setting something up here, so if you have any questions, you could bring it up. Okay. Okay. All right. So thank you. All right. So our task is a very simple one. Now, the notes I made here, I've made it almost like the things I'm going to say. Okay, so that when you read, at the beginners in particular, when you read, you can really uh, get into my mind to know what I'm trying to talk about. Okay. So our task is a very simple one. Okay. For all these 36 hours is just to perform something very simple, and that thing is to design a circuit for the Atmega 328 microcontroller. This is the version that we'll be designing for. Now, I think Atmega 328 comes in three different versions. We have the, I think I have used the surface, two surface mount versions. One is a QFN and the other I'm not very familiar with. But in this trading, we are going to use this particular DIP. Okay, DIP stands for Dual Inline Package. So, what are some of the things that we'll be doing? That is everything that we'll be doing in the next 36 beautiful hours. Okay. So basically, we will be creating a circuit, and the dictionary meaning for a circuit is some path or circular line or route that so there is a starting point, there is a finishing point. It basically forms something like a closed route or path. Okay, basically dictionary definition. Quickly, let me check if somebody is waiting. This is really going to be something else. Yeah. Okay. So but in electronics, when we talk of circuit, then we're going to look at the path that current flows through. Okay, the path that current flows. And I know definitely everybody on this platform right now has an experience with a circuit. At least you've seen how a light bulb works and that kind of thing. So I'm hoping we wouldn't have to. I'm hoping we don't have like an absolute newbie among us. Okay. Now, every circuit that you build has at least three basic components. Every circuit has at least three basic components. And these are actually required to function. Now, the first one is the source of energy. A source of energy because the circuit will require some form of energy to work, and that means every circuit that we build has to have a source of energy. The next thing that is required is an active or is a conductive path. A conductive path. Remember, we said the circuit is supposed to be something like a path for electrons. So if we have some energy, we should also have a path for this energy to conduct. And finally, there is always some form of load that receives the energy that we are trying to transmit. Okay, so the energy that we need is actually because of the load that we want to power up or turn on. Okay, all right. So if I have, let's say, a 3-volt battery and if I have, let's say, a 3-volt light bulb, okay, it could be, let's say, a green LED, a green LED, a blue LED, or a normal light bulb, and I hook it up to a 3-volt battery. That is very simple or very basic form of circuit that anyone can build. Okay, so in general, building a circuit, every simple or basic circuit is just a source, and the load. Then these black things that we have here are the conducting part. Okay. Now, usually the main thing that determines every other thing is the load. Okay. The way the source you choose, the nature of the source, as we'll be looking at very shortly, everything depends on this load. Okay, so we build a circuit because of the requirements of a load. You don't build your circuit and later think about your load. Okay, there are, I mean, few instances if you are designing for a generic situation, yes, you can do that, but in most cases, you have to design your circuit because of the load or the requirements of your load. Okay, so basically everything that a designer is supposed to do sits in between this. Okay, the designer's job is to make sure that the energy which is from the source is transmitted to the load efficiently without a lot of losses. James, why is James presenting? Please, uh, let's try as much as possible not to be interfering with the slide share. Okay, I'm controlling a lot of things I may not notice, and a lot can go wrong. Thank you. All right. Please just a minute. Okay. Thank you. All right. So circuit designers work is in between here. Everything that would make this load works. That is what we are about to look at. Okay. Now, just before we get continue, there are a lot of other forms of energies, right? We all know of things like sound energy, mechanical energy, potential, kinetic, and all those stuff, right? But have you ever asked yourself why we use electric energy for circuits? Anybody has an answer to this? Why we prefer electric energy in we depend so much on electric energy instead of the other forms of energies. Anybody to give us an answer to this? Have you ever thought of it? Why is it that we decided to spend this so much time on electricity? Please, when you join, you try to mute your microphone for us. Okay. Now, it happens that electricity, okay, so I have somebody trying to answer. Yes, let's hear you.
I think they are using electricity because it's easier to control and manage.
Really? Okay. Easier to control. Okay, fine. That's cool. Any other suggestions, Joel Adu and Hassan? Any reason? Yes.
The rate at which
The rate at which,
they travel.
so that is to deal with the speed, right? Okay. I mean, sound would do like 340 meters per second in normal atmospheric condition, right? So just imagine you are supposed to transmit data from, like, as we are streaming right now. I'm in Ghana, somebody's India, another person is elsewhere, right? And we are working with sound. Now, sound has to travel at best around 340 meters per second, right? Just look at the distance from Ghana to, let's say, Kenya. That means you probably have to listen to my words in like 2 weeks' time. Or that's just to exaggerate. So the speed of electricity is actually a thing. Any other? Any other? Why do you think we rather prefer to use electricity instead of the other forms of energy?
The materials that we use are conductors of electricity.
Okay, fantastic. That is good. All right. So there are a few things that makes electric energy preferred over the others. Okay. Now, one, as somebody already said, is how fast it travels. Okay. The energy travels at the speed of light. Take note, the energy I'm talking about is an electromagnetic energy, right? And it travels at the speed of light. Okay. So that is why these things are all possible. I am in Ghana, somebody's in India, somebody's in Kenya, but we are still able to communicate in real time. Just as one of the the reason electricity is what is preferred. Another reason is that it's silent. Electricity is silent. I mean, you could hear a few humming sounds from the 50 hertz AC, but that still doesn't compare to the sound these something like sound energy. What sound energy could produce? Okay, so it is very silent. Another thing is it can be transformed to and from other forms of energy. So you can see that maybe in your country you depend on hydroelectricity. Okay, some people may depend on renewable energies like solar panels, windmills, and all that. In all these generations, power generation mechanism, you realize that we are converting some form of energy to electricity, nuclear energy, geothermal. And the beautiful thing is that once we get the energy back into electricity, we could also use some devices called transducers to convert them back to other forms of energy. Okay, so we can always convert to and from other sources of energies. Okay. Now, another interesting thing is that we can store electricity, right? Right now, probably some of you are on batteries, others are on laptops, and your laptops and sorry, some of you are on mobile phones. Your mobile phones are battery powered, right? You could transmit it, you could take it anywhere with you and still get your electricity with you. You can talk of batteries and power bank. So this is an ideal thing that makes it preferable. That makes electricity preferable. And again, it can be transported over a very long distance. Okay. For instance, where I am, I think my electricity production is about a whole region away from me. Yet when there is lights on or off, you can receive it in almost an instant. Okay, so these are some of the reasons we prefer to use electricity. Okay, now the next question is where can we get these energies from? Now I'm doing these fundamentals because of our newbies. Okay, so please, the senior men, just be patient with me. So we know of batteries, we know of solar panels, electric generators, wind turbines, and all that. Okay, I have been talking about electric energy now, crudely, and I'm saying crudely, emphasized and crudely in quotes. I'm going to refer to this energy as voltage. And again, let me stress on the fact that I'm doing this crudely because I don't want to go into the boring theoretical stuff. Okay, I don't want to bore you with all that. So for now, take it as we get voltage, or we are going to, in anytime I talk of voltage, I'm referring to the electric energy. And once again, please pardon me, I'm talking about this crudely. Okay, so take note of that. Okay, so we are crudely going to refer to the electric energy as voltage. Okay, and anytime we see the letter V anywhere, that we should know that we are talking about what? Voltage. Is that okay? Now, the voltage of a battery or any energy source can be measured using devices like an ohmmeter, sorry, a voltmeter or a multimeter. How many of you own a multimeter? I know probably most of you do. Okay, so if I take any battery, I can actually check its voltage. That means, roughly speaking, uh, what driving force it has. Okay, well, then sometimes you can see batteries rated as 9 volts, 12 volts, 3 volts, 3.6 volts, and so on. Is that okay? So crudely, and I keep repeating this, let us assume that this voltage has something to do with the energy of that source. Okay, every energy source, so on here I have sample batteries, right? Different types of batteries, but at least every energy source will have two terminals. Okay, and these terminals are usually labeled positive or negative. Okay, so if you look at where these blue arrows are pointing, they are showing you the terminals of these types of what battery. Now the terminal is just the point where you connect your conducting wires. Okay, so for instance, if I want to measure the voltage of a particular battery. If it is this kind of battery, this is how you do it. You take your voltmeter or your multimeter, connect the COM to the negative side of the battery, and the voltage terminal or pin to the positive side. So this is how you test the various kinds of battery, just for the beginner's sake. Okay. Now, circuit designers, what we do as part of our duties is most of the time not a simple task. Okay. Now, let's take a very simple situation, a very simple scenario. Uh, there are instances when you may have to craft or turn on, send energy to, let's say, a 3 volt bulb, right? But then the battery that you may have could be a 9 volt battery. That means in this case, the energy is more than what the load requires. Okay. Now, there are times where the energy that you have. So let's say I have a 3 volt bulb, but my battery is a 1.5 volts battery. Okay. So in this case, the voltage is less than. Please, when you join, kindly mute your device for me. Thank you. Okay. Now there are few instances where your battery's voltage would meet the load that you want. Okay. Now, if you look at the different types of battery technologies, you can see that they come in certain voltage standards. So you can see something like 1.5, 3 volt, 9 volt, okay, in that order. Now, usually this depends on the technology used, okay. So most of the time, yes, you have to do with these first two situations, energy being more than is required, energy being less than is required, and when you are lucky, your energy would be exactly as required. Now, usually this third case is the easiest you can get as a circuit designer, okay? And no matter the situation, in all these three cases, as a circuit designer, you can actually solve the problem. You can actually design a circuit for it, and we shall see how very soon. But trust me, there is that particular situation that you can't do anything about. So you just have to sleep, probably talk with your client, and then find another means of doing that. Okay. We shall look at all these things. Now, let's take a look at a very simple circuit. Probably most of you are already aware with something like this. I have a battery, I have a light bulb, I connect a wire to one side, one terminal of the bulb, and then connect the other terminal to the battery. I get this bulb to lights. Okay, so we have an energy source, we have a conducting path, and we have a load. Okay, so this load here is usually any device, the things that we refer to as loads in circuit. They are usually devices that require electric energy to operate. And I've been talking about light bulbs since we started. What other forms of energy and loads, electric loads do you know of? What other sorts of electric loads do you know of? We can talk of a speaker, a DC motor, a heater. Any other source that you can think of? Any other source? Okay, just type it in the comment box. Okay. If you take a typical circuit, okay, for instance, what we have here, we have our source, we have our load, and we have a switch. We could eliminate this switch and all the time disconnect our battery, our energy source, okay, to switch this on or off. But as the name implies, the switch is in here to make the work super simple and super easy. So we just turn it on or off to make or break the circuit. Okay. Now, the battery, the wires, and the switches, everything that you are seeing here, we refer to them as circuit elements or circuit components. Okay. Now, usually, if you assuming you have to design a very complex circuit and you have to be drawing things like this to represent your circuit, I mean, this is way not convenient. Okay. So what we do is that there are some special symbols that have been crafted in the electronic industry to represent any electronic component that you can think of or you can use in your circuit. Okay, and these special symbols, we call them circuit symbols, and we'll be looking at them here. Okay, so by using circuit symbols, I can just convert this uninteresting diagram to something very romantic like the one I have here. Okay, so I'll replace my battery. By the way, a battery is a collection of cells, right? So technically this is just a cell, but I'm going to loosely call it a battery. So I'll replace this battery with this symbol. That's the symbol for a battery. This bulb here, I'll replace it with that. This switch will be replaced with that, and these lines here represent the red wires that you are seeing over here. Okay, so going forward, instead of dealing with this, we would be dealing with this. Okay, now each component has a unique circuit symbol associated with it. So there is a symbol for resistors, for inductors, capacitors, and any component that you can think of. Okay, however, when it comes to how the components are drawn, there are two schools. We have the international standards and the North American standards or versions of the components symbols. Okay, we will look at them when we start doing our schematic capture. Okay, so whenever the load is connected, we would have energy flowing from our source to the load, because primarily that is the thing that we intend to achieve. Okay, however, you see, this energy that is flowing is in the form of electromagnetic waves. And actually, if we want to deal with this energy in that electromagnetic wave state, we would have something called Maxwell's equations to deal with. And trust me, you don't want to do that, right? So what we intend to do is to rather work with the effects, okay, effect of the movement of the electromagnetic waves. And usually we can detect this effect as a form of, as something called current, okay? So when energy moves, current is observed in the wires, okay? This entry thing, whenever there is a movement of energy in the circuit, one way we can notice that is that current will begin to flow in the wires or within the circuit. Is that okay? Now, just a quick one. This current that we are talking about, okay, it's as a result of the flow movement of some tiny charged particles we call electrons. If you are interested in the nitty-gritties of these things, I'm not going to go into that details. You can check out my tutorial on Phatronics. It's on Tech Foundation Africa's YouTube page. I talked so much on these basics. Okay, you can check those things out. But for now, just know that inside the materials and the conductors and the components that we are using, there are some tiny particles called electrons. Now, when these particles experiences energy, when we apply energy to our source, or sorry, our circuit, these particles begin to move in a particular direction, and this motion is what we refer to as what? Current. Okay. Now we can easily measure this current, and fortunately, there is a way to relate it back to our electric and magnetic fields. So it's just convenient to work with current instead of dealing with the electric energies, the EM waves themselves. Okay, so usually these electrons actually move from the negative terminal. Okay, the flow is from the negative side to the positive side. Okay, however, conventionally and per historical means, we usually consider current to flow from the positive to the negative terminal. Okay, so take note of that. However, in real sense or in real life, the electrons are actually moving from the negative terminal or the lowest potential to the highest potential. Okay, but usually we would just we would talk about it conventionally as moving from positive direction to the negative. Okay, all right. Yeah, we will soon be done with this basics. Don't worry, we will soon be done. Okay. So when electrons flow, we call it current, and conventionally, like I said, we take the flow to be from positive to negative. Now, the current, we can measure it in units of ampere, or usually abbreviated as amps, and the ampere is symbolized by A, the capital letter A. Now, usually we would like remember when I talked about voltage, I said that we would symbolize voltage with a capital V. For current, we are going to use an I. Okay. Now, the rate at which our energy source moves these electrons or the current about in the circuit is a quantity that we refer to as power. Okay, if you have a physics or a science background, power, we say that power is the rate at doing work. Okay, and mathematically, power relates to the voltage which is coming from the energy source and the current which is moving due to the energy source by this relation. Okay, so the product of your voltage and your current will give you the power of the circuit. Okay, so let's say I have a system that is powered by 9 volts and there is a current of 1 amp moving through this system, then I have a power of 9 times 1 amp, which is 1 watt. Power is measured in wattage. Okay. Now, please take note of these things. We will need them when we start creating our circuit. That's why I want to talk about them briefly. Okay. Now, the sources of energies that we could use, they come in very different forms. Okay. There are some sources that keep changing their positive and negative directions, or let me call it keep changing their directions. We call them the alternating current sources, right? So that's say, let's say at one point, if I have this as my negative terminal and this as my positive terminal, at one point they swap. Okay, not like physically swapping, but the polarity changes. So the one that was previously positive becomes negative, and the other was previously positive, negative becomes positive, right? Now, a typical example is the AC sources in our home, right? If you take the live wire and observe it, you realize that it keeps changing polarity from negative, positive, and sources like that, we call them alternating. Now, please take note, usually it is sometimes I find people referencing any time varying voltage or current as alternating. Please, it is not alternating until there is a change in polarity. Okay, it is the changes in polarity that makes it alternating. We could still have a time varying voltage, but so far as the polarity is not changing, it is not an AC source. Okay, so if you take your voltmeter and or plug something into your home socket, what you're going to get is a typical example of an AC power. Now, this diagram here is to give you a clue about what is happening. So in a DC source, direct current source, so for the direct current sources, they don't change their polarities. The polarity stays the same. So if this point is the positive, it remains positive throughout the life cycle of the circuit. Okay. So here we have current always moving in one direction, okay, always moving in one direction. But for the AC source, you can see that it goes one direction briefly and change to the other direction. This is because the polarity is always changing, so does the direction of the current. Okay. Now, usually in electronics, we prefer DC sources. Okay, we prefer DC sources. Exactly, example what we have in batteries. Okay, so that means that if you are a designer and you have to use an AC source as your power source or energy source, then an additional task has been added to your work. Okay, first of all, you would have to convert the AC into a DC, because mostly in electronics we want to use DC sources. Okay, And aside that, if you take a typical home, source, a voltage source, in some countries you get something like 110, 120. In Ghana, we have 220 to about 240. Okay. Now, this is a very, very, very high voltage. Okay. So let's say I want to charge my battery, my phone's battery. My adapter would have to, when I plug my adapter into the source, into the socket, what happens is that the adapter first converts this AC. Okay, it converts it from AC to DC, and also step it down from the 220 volts, for instance, to 5 volts. Is that okay? So the adapter is doing all that task for you, and probably you have no idea that that is happening. Now, when you change an AC source to a DC source, we call it rectification. Okay, the process is called rectification. All right, and like talking about the adapter situation, so anytime you slot in your adapter, know that there is rectification going on. Your voltage has to be converted from AC to DC and then step down to the right amount that your load requires. So that is the reason you always need a socket, an adapter for your socket, but then you don't need an adapter when you connect your phone directly to, let's say, your computer's USB port, okay, because the USB port is already providing the voltage level that your system requires, which is DC and at 5 volts. All right. So now that we know about these voltage sources, let us go back to our key card, and now we know what to do. We are going to first place our voltage sources and then continue from there. Now, as I do this, if you have any questions, please feel free to ask. If you have any questions, feel free to ask. Okay, so what we're going to do right now is to put some power sources. Right now we know about power sources and so on and so forth. Is that okay? So open my key card in here, open the schematic. Now the first thing we have to do, or I usually do, is to let KeyCard know where my power is coming from. Okay, and in KeyCard you do that by using what we call power flags. Okay, power flags. So to place a power flag, Arduino board technically should be able to withstand from about 7 volts to 18 volts. Okay, now we will talk about why. Yeah, if you have any questions, please go ahead.
Yeah, I think we can take maybe 5 minutes break to attend to the questions. I can see some hands are raised on
Oh, okay.
on
Okay.
the queue, and also some questions on the chat.
All right. Then thank you very much for drawing my attention. Let me quickly switch and then let's have some. If you have any questions, if you are a senior member and you want to chip in anything, please, you can always come add up to my answers. Yes, please. Hello.
Hi.
Yeah.
Please, my name is Joshua.
Okay, Joshua.
Yeah, and then you mentioned that not every pulsating energy source is AC.
Yeah.
Yeah. Can you please explain further?
Okay, so I wish I had a diagram here. Okay, so when we talk of AC, okay, the main idea is that there is a changing polarity. Okay, so say in simple terms, it means that if I have, let's say, two terminals, one representing positive and the other representing negative, okay, at one point the positive will become negative, the negative becomes positive. At another point, they swap. Is that okay? Uh, Wow, I wish. Okay, let me just do a crude sketch over here. Okay, so I'm drawing something. I'll show to you briefly. In the next session, I'll bring my tablet so that I can do some of these things. Okay, please, can you all see this? Can you all see this? right? Sorry for the. I just I just have to do this quickly. Okay, so exactly. So over here we would have a positive voltage here and a negative voltage. So all right. I'll bring my tablet next time, don't worry. So you see, when the source is within this quadrant here, right? You realize that the voltage is positive. Is that okay? But when it comes down here, the voltage becomes what? Negative. Now you could have a pulsating something that looks like an AC, but would completely be inside the positive quadrant. In this case, it is just a time varying voltage, but it's actually not AC because its polarity doesn't change. The key word here is the change in what polarity. Is that okay?
Yes,
All right. Please, any other questions? Any other questions?
please, I have a question.
Okay, please go ahead.
Okay, please, let's say that a PlayStation machine.
Let's say that
The
your voice is not very clear.
Oh, okay, let's say that a PlayStation machine
Okay.
it takes AC. So if the polarity changes, and how will you plug the adapter to turn it
Okay. This is very interesting. Now, thank you for the question. Let me also, in fact, please give me just a minute to bring my tablet. Okay, I think I would need it. So just a minute. Okay, thank you.
on? Mr. Obin,
Yes, please.
Mr. Obin,
Yeah, I'm listening.
okay, so while you are away, let me help you explain it.
Okay.
I'm saying while you are away, let me help you explain it.
All right. Sure. That'll be okay.
Yeah, so one was the question. One was the question asking if the polarity changes, then how do we plug the adapter? How would I get the polarity, how you turn on? Yeah, so the polarity does change. So we mentioned earlier that there's a circuit in there that takes this changing or alternating polarities and then rectifies it into the form that has been changed. So that's the form that the main circuit of the AC switch takes and then works with. Are we clear? So that's the polarity does change. But there's a rectifier circuit in there that puts in that alternating boost circuit and then transforms it into a DC form that can be used by other person. Are you clear? Yeah, I understand.
Okay. Thank you. Yes. I hope the one who asked the question got the answer he was looking for.
Yes, I got it.
Okay. Just yes. So quickly, just to clarify things. Okay. I think I had a lecture somewhere sometime and I had to spend so much time explaining these steps. So quickly, I'm going to do that again here. Let me share a whiteboard. Okay, share, allow everyone. Continue. Okay, please can you see the whiteboard? It's not visible. Okay, I think I may have to do some swapping. Okay, present this view. Okay, Please, can you all see the whiteboard?
Yes.
Okay,
Yes.
so fantastic. Uh, Unfortunately, I can't work on the whiteboard here. Okay. Uh, how do I do this? How do I do this? Just a second, please. Admit all. All right, let me stop sharing. Oh, no. Oh, sorry, I mistakenly took myself off. Okay, just a quick one. Yeah, I'm here. I just came back. So many settings going on here. Okay, now let me. I'll join you. Thank you. All right. Okay. Hide this. Okay. So thank you for your patience. I'm going to share the whiteboard again.
Please, the one using the root account, can you off your camera, please?
Okay. Okay. Yeah. Let's use this and then share the whiteboard. Where is my whiteboard? Oh, come on. What? Okay. Yeah. Please, can you see the whiteboard now? Can you see the whiteboard? Hello? Please, can you all see the whiteboard? All right. Hello. Please, can you all see the whiteboard? I'm sharing the whiteboard. Can you all see it?
Yes, we can.
Okay. All right. Good. So we have
Yes.
something like this. Okay. So I'm going to try and explain the concept of this AC thing. Okay. I think it will help a lot. Okay. So I just did not respond. Okay. Oh, please. Find this group. Okay, good. So this is something that is going on, okay, for the sake of those who want. Uh, so I'm going to. Oh, come on. Let's draw this graph here. Simple representing. This is time, right? This is time in second, and then we have voltage. So this is the positive side of the voltage, and we have the negative side of the voltage, right? And this is our origin, 0 volt. Okay. Now, when we say that a voltage source is AC, okay, it means that probably if we start from ground, it rises to a peak value. So if you are in Ghana, for instance, this peak value could be somewhere about 240 volts. Okay. Now I'm not going to go into all these things called root mean squared and stuff. Just some briefing, right? Then it falls, okay. Then as it falls, it now crosses into the negative zone. Now, what this means is that if let's say uh, for that particular source has two connectors, a positive and a negative connector, right? At the point where it is in the positive quadrant, let's call this the positive quadrant, this will be positive, that will be negative, right? But when it switches, then this now becomes the negative and this becomes the positive. Is that okay? It is only when this happens that we refer to as an AC, an alternating current. The key word is the change in polarity. Is that okay? But we could also have, let me change the color. We could also have something that is doing this sine wave character, but then it doesn't cross into the negative zone. This is still a DC voltage source, okay? Although it is what? Having some varying, usually in the DC we call it the ripples. Is that okay? So take note of this. Now, about the guy who asked about the PS2 thing, right? For our AC mains, we usually have like three wires coming into three wires in our homes. We have the live wire, we have the neutral, okay, and sometimes you have the earth, okay. Now, this is usually what is coming from your transformers, your substations, okay. Now, take note. The up and down swinging, it's all on this live wire. It's this same cable that is doing that. Is that okay? But what happens is that when the AC enters your PS2, okay, like my brother Riley said, most in fact, if I am bold enough, I would say that every electronic component works with a DC. Okay, so what happens is that your inside your PS2 there is a rectifier circuit. Remember, I said that the process of converting AC to DC is called rectification, right? So there is a circuit for rectification that converts this AC to a DC output that your PS2 depends on. Is that okay? So technically, yes, you are tapping from an AC source, but the conversion is done internally and the circuitry of your system depends on the DC output. Please, is there any other question on this AC thing? No. Okay. All right. I want to close it. Any other question that will need a whiteboard explanation? Okay. Yeah. Yeah. I think this is good. This is good. Yeah. Any other questions? Any other questions? Any other questions? All right. So let's now that we know of our sources and we know that every circuit that we build would require a source one way or the other, let's quickly switch to our key card and see how we handle sources in key card. And before that, let me clear this stuff. Wow, how many of these did I open? Okay. Let's just okay. Wow. Thank you. Please, I'm still doing some switching. If you have any question, you could go ahead and ask, or either myself or any other senior member can help you answer that. Okay, so let me stop sharing and then now share a window. Okay, all right. So in back in KiCad, now what we have to do is to place our connectors. We have to show KiCad where to get power or where the power is coming from. Is that okay? To do that, you need to add a power port. Is that okay? Add a power port. Now, I'm going to define various power ports. Now, I think we'll be using about 3 different going to define well, We really have to figure out how to do this co-admin thing because it's not convenient for me now. Okay, people keep joining and sometimes I don't see it. All right, so the first power source that we're going to put, we call it VCC. Okay, so KiCad already have a lot of these already set up, so I'll choose VCC, and this is going to be a universal power source that's going to represent our power input. Okay, now I could choose to double click on it and change the name to maybe VIN, as we usually see. Oh, actually it's not editable. Okay, so keep it VCC, but in our mind we know that this is the VIN. Okay, the external power that we will be connecting to our board. Is that okay? The external power. Then we need a 5-volt source. So I'll pick my 5V, put it here. And then finally, we need a 3.3 volts source too. So let's put that one to over here. Okay. Now you press on M, the key M, not Shift M or any other. Just press on M to move something. Okay. So anytime I want to move something, it's called a hotkey in KiCad. You just press on M and that thing you can drag that thing along. Okay. Now, usually when you do this to avoid certain design rule checking errors, what you do is you have to do something like a power declaration, right? To do that in KiCad, I'm going to bring up something called a power flag. Power flag, and rotate it. I rotate using R and realign it over here. Okay, then press Ctrl D to duplicate, Ctrl D again to duplicate. Okay, so if you are a programmer, this is similar to variable declaration. We are telling KiCad that, hey, we have power coming from somewhere, and take this thing as a power source, port that we'll be getting our power from. Now, there is one more that we have to place, which is the ground. Okay, a ground in circuit is the point of convergence of currents. Is that okay? So usually we say that it is the 0 volt, or in terms of battery, we refer to it as the negative terminal. But any point in your circuit where current will be converging. Okay, so take it as anytime current moves from anywhere, that is the last stop for it. That's what we refer to as ground. I'm going to put a ground here. To do ground power flag, you use something, another special type of power flag called GND power. Okay, use this to create a ground power flag. So like that, press M to move it about. You can hold Control to have a finer tune. Press M to move this about. And again, by default, when you hover on a connection point, the wire tool should be enabled. However, you can always select the wire tool by pressing on W or pressing on add wire, and you can safely do that over here. Okay, so I usually pay attention to the aesthetics of my schematics. So yeah, and what I usually do is draw a very long header here. Okay, and you can always double click, right click on it, and then set the width. So I'm going to set it to 0.5. A lot of people are around. Let me admit them. Okay, set it to 0.5. And what I'm going to do with this is, let me do some editing. I'm going to select that, no dash. Let me set this one to 1. Okay. Whoa. Mils. Okay. So I want 1 mm. Now take note here. By default, the unit is mils, right? But if you have any value and you need it to be, let's say, mm, right? then you could just type the unit with it. KiCad will automatically do the conversion for you. So if I do that, yeah, this is now too big for me, so zero 0.5 mm, and it automatically convert it to mils for you. Okay, and I usually put a very nice header. So let's call this let's route uno circuit diagram. Okay. This is not necessary. It's something that I usually do, and I'll set this to 5 mm. Put it here nicely. Please, again, this is not necessary. I just do it to make my circuit look somehow nicer. Okay. All right. Now I can edit this, set it to bold, and I'm good to go. All right. So down here, now come on. Select this power flags, move them below, and again, somewhere this up there. Give it a label. This session is supposed to end so 9 to, oh, we still have time. Okay, so I'll call this power flags. I'll give it a title, power flags or power quotes nicely, and then set this to maybe 2 mm. Put it here, and again, this is not necessary. You choose to do it if you want probably to beautify your circuit. Okay, so I'll do that, and then usually I put this on bold. Yeah, let's just leave these guys there, and then round this up like that. Okay, it's just a way I use to easily identify the sessions in my code. So now we know this could be coming from a battery, but this is like the main input. This 5 volt too, there are two places that we'll be taking it from. We will look at that very briefly, where we are going to get our power. But in total, what we have done right now is we have declared our where our power is coming from. Okay, we have declared where power is coming from. My PC is running so slow. That's why it seems to be dragging stuff. Okay. Okay. Good. Now that we have done this declaration, let's actually start placing the power component. Okay. If you take a typical Arduino, trying to pick one, you have the power port that is used. It's called a DC barrel. Okay, so let's quickly place a DC barrel. To place a DC barrel, we need to go to add symbol. Okay, go to add symbol. Forgive my PC, it's running so slow. I think the memory the memory is really struggling. Okay, but we move. Probably let me shut down this PowerPoint. Okay, come on, don't waste my time. All right. Yeah, I can see a hand up. Joel Adunyame, please, if you have a question, you can go ahead as I wait for the things to load. Things will get interesting very soon. Things will get interesting very soon. Okay, please, if you have questions, let me know. That's the next minute. If you have questions, let's hear them. Okay, let's hear them. Please ask before my library finishes loading. KiCad doesn't take this long. Okay, I'm having this challenge because I'm running a lot of software programs on my machine right now. So if you have any question, please go ahead and ask. Oh, come on. Okay. Yes, if you have any questions, please. Any questions, please? Uh-huh.
I'm experiencing a certain problem with my keypad.
Okay.
It's the appearance of the schematic editor
Mm-hmm.
has some green lines. I wanted to know if it's a norm or there's a problem with the installation.
Is that it has some green lines or
It's all over.
all over, and you didn't put that on?
Yeah, I did.
Uh,
I just finished installing it and it came back
well,
again.
technically, it shouldn't be doing that. So let's see, maybe, uh, unfortunately, all right. It's try and restart it and see. Okay, try and restart it if that solves the problem.
Sure.
Okay.
Okay.
Okay. All right. Finally, it came. Okay. So we any more questions, please? Any more questions? Any more questions?
Could you kindly explain the difference between LT space and KitKat?
Oh, okay. So
Because currently,
okay, okay. LT Spice is actually a program for simulation, circuit simulations. Okay. KiCad is more of an EDA, electronic design automation. Okay. So take KiCad actually has some of the functions of LT Spice in it. Okay. I think they use NG Spice. So Spice programs are usually used for simulations. Okay. You can't actually use that for what we are using right now. I don't know if that explains things to you. You could use it to capture a circuit.
thank you, thank
Yeah, you could use it to capture circuits, all right, but you usually use them when you want to simulate your circuits, not design PCBs. Yeah. Please, any other questions? Any other question? Just 1 minute, then we continue. Any other questions? Sorry for all the interruptions. Okay, I thought all these settings were done, but I had a lot of challenges today. After this, we're going to fix all that. Yes. Any other question? Okay. All right. So somebody actually also gave an answer in the one who asked about the LT spice. Somebody gave an answer in the what do you call it? The chat session. I think it's also a very brilliant one. Check it out. Okay, so we're going to place a power port, the DC barrel, right? So all you have to do is to type DC. Now, for keycard, mostly you would have to know the component's name in order to search for it, else you would really struggle a bit. Okay, so DC barrel. Okay, so you can see that there are DC barrel jack connectors here. That means that it is under the connector library. Okay, but if you look at it, be careful when you are choosing the symbol. Okay, this one has just 2 pins, but the barrel we are looking at using actually has 3 pins. Okay, and so you have to scroll through and then look for. So this is a typical barrel that I am looking for, right? So I'll double click on it and then place it on my circuits, on my schematic. Okay, all right. Now you can always press on E while to edit the component values, or right now I can just press on V to edit the value specifically. So I'm going to call this power port, this PWR port. Okay. All right. So this will be my power port. Now, one thing too, every component has pins. Now, there are some components that are polarized. If we say that a component is polarized, that means that it has a specific pin dedicated for positive connection and another for negative connection. The moment you interchange these things, you are going to create problem. Okay. Now, I happen to have used these pins so much, so I know them, right? I know them by heart, right? So if this particular component, then pin one is actually what connects to the positive power, okay, and 2 and 3 connects to the ground. Now make sure you don't actually interchange this, else you have issues. Is that okay? So what I'm going to do is connect connect. First, I'm going to connect the ground. Okay, going to connect the ground. Now both pins 3 and 2 connects to ground. So I can come here, Control D to grab the ground net and put it on that. That means I've connected this to ground. So take it as I've connected this to the negative side of my battery. Is that okay? Now, what do we do with the positive side? Usually, what I do is attach a very small. Okay, I won't go there right now. There will be time to talk about that. Okay. I was going to talk about capacitors, but I have another session for that, so I'm not going to talk about it right now. Okay, so the next thing is to connect a cable from this. However, we need switches? No. We don't have to put any switch on this. But then we need actually to protect this particular circuit. Okay, there are times where somebody may mistakenly do the connection, and so we have something called the reverse current protection. So we are going to do some reverse current protection. Okay, for now we will do all that, but let's just go ahead. I'll do those things as and when they come up. Okay, so I'm going to mount our power net, which is the VCC, on this. Okay, so the moment I do that, what has happened is I have connected the power, I've connected this pin as my VCC. So anywhere in circuit that I reference VCC, what is going to happen is that the circuit is going to connect to this point. Is that okay? And we will see it clearly later. Okay. Now, remember, this source that we are taking from here could be any voltage source from 7 volts to about 18 volts. That's the recommended voltage for Arduino. Is that okay? However, the Atmega IC that we want to use cannot operate on this voltage. Now, one thing that we need to know how to use is the data sheet of the components that we use. So quickly, I'm going to bring up the data sheet for Atmega, the Atmega IC. The way you do that is just search for it. Okay, so Atmega 328P 328 data sheet. Okay, just a Google search should do the magic for you. All right, so you can see that it's a product of Microchip. So let's grab it from here. Okay, now let's look at the parameters, the voltage requirements of what we want to do, because now we have brought our voltage source to the schematic, but we don't know about the requirement. So this I'll quickly switch to power consumption, not here, operating voltage. So the IC can actually operate between 2.7 volt to 5.5 volt. Okay, this is the operating voltage. However, it is usually we build this for 5 volts. Is that okay? So we are going to power our Atmega with 5 volts instead of the 2.7. Okay, you can look into how to do that later. But right now we are interested in powering this up with a 5-volt source. That means that whatever voltage that we bring in, and this voltage could be anything, it could be 7 volts, it could be 9 volts, 12 volts. We have to make sure this voltage is, we have to make sure we are getting a 5 volt out of it. Okay. Now, to do that, we need a component that, we need a special component that can step down whatever voltage that we put in and produce an output of 5 volts. Is that okay? We call this voltage regulators. And for this project, the voltage regulator that we're going to use is an LM7805 IC. Okay, so I'll go inside my library and pick set for 7805. Okay, so if you read about it, see it's a linear voltage regulator. It can source up to about 1.5 amps, and it can handle a maximum of 35 volts. Please, when you enter, try and mute yourself for us. Okay, so it produces a fixed output of Hello, please mute your mic. Why am I not able to do that? Hello, Eddie. Eddie, please mute your microphone for me. Somebody should draw his attention for me. I'm not able to mute it. Okay, thank you. So this is exactly what we need for the job. We need a 5-volt output, and we want to ensure that it's a fixed output, and the current that it can generate or it can source is also quite appreciable. And if you look here, it can deal up to about 35 volts, which is all good for what we want to do. So we'll bring this component in here, okay, and then connect it. So you see that it has 3 pins. It has pin 1 as input, so we connect the input pin to the VCC, which could be the battery or whatever source that we are using. And we also need to connect its ground. Every component that you connect usually should have a way of tying itself to the rest of the circuit. And then the output of this guy is where we will get our 5 volts power or voltage source. Okay, so I'll put it like that this way. So now let's see, we have our VCC checked, we have our 5 volt checked, and we still have a 3v3 voltage to deal with. Is that okay? So let's handle that before we proceed. Don't worry, I have intentionally left out some things I'll be filling in as we proceed. Okay, so the next thing is to find a means of generating a 3 volts. Now, we are not going to put all these voltages differently on the Arduino board. All we need to do is to supply the VCC, which could be a 12 volt, and out of it, we are generating the rest of the voltages. That's what we are trying to achieve here. Okay, so we will also need another component, and this time I'm going to pick AMS 1117 3v3 version here. Okay, AMS 117 3.3. Now again, please don't be alarmed. I've been working with these things, so I know them. Okay, sometimes if you need a component, just Google 3.3 volts or so, and so you get a lot of answers. But I know these components, I've been using them. All right, so let's place this. It's also a linear voltage regulator, just like the first one. Okay. Now usually I won't do this, so let me disconnect this and do things as I normally do. All right, so put this guy over here. Probably just squeeze this in, and then put that here, and that there. Okay, we will put the label. Just put it in. Let's call it DC barrel interface. That's DC barrel. That's okay. DC barrel. Right. Then the next stage is going to be my 5 volt regulation. Please, these things that I'm doing right now, they are just my choice of designing circuit. Okay, I'm not saying we're doing the same thing. Okay, so put this here, move that there, and then please, if you have any questions, you can ask right now as I do this arrangement. If you have any questions, yes, go ahead. Now look at something. Anytime you are doing your connection, okay, try and make sure there is at least a gap for you to see that there is this green line. The green line here represents the net. Is that okay? Now, actually, if I don't do that and just move this to snap, okay, technically it's connect. However, there are cases where I've seen things like this, but they weren't actually connected. Is that okay? So to be on the safer side, always just make sure you can see at least this green line there, okay, to show you that these things are properly connected. It's better that way. All right. I want to move this up. Okay. All right, and then yeah, so I can still answer your questions. I can still answer your questions. Okay, and again over here, what I'm doing is yes, sir.
Okay, so it seems like you are going to prioritize the animation, PowerPoint, the way you do it.
Oh, okay.
Can you
All right.
have the easy the lines and then can you just
Okay, so basically what I'm doing is just rearranging, right? This to do the text, this is the T. You use the T, add text for that. This lines you use add graphics. Okay, so yeah, basically just I haven't done anything extra. Now take note that I am intentionally leaving this space here. We will fill it up later. Okay, and then let's put our 5-volt VCC in here. All right. So I know that my 5-volt regulator takes in the VCC and produces the 5-volt output, constant 5-volt output. Okay. Let's do the same thing for our 3-volt regulator. We're going to move this a little bit down. Yes, sir. Come again. The DC bar. Okay. Let me see. I should probably get Arduino board around. Okay. Switching to the camera view. All right, can you guys see me? Can you see the Arduino board? Can you see me? Can you see the Arduino board? Okay, good. Is my feed mirrored? Is my video mirrored? It's okay, right? Okay. All right. So this here, let me take it closer. The one who has the question, this thing here, okay, this component here. Probably I'll just show you on this the component on Arduino board. That's the DC power. Let me just put it up on the internet. Okay, that will be better. That will be better. Okay, I'm doing so many controls here. What do you mean? Okay. Okay. So let me just pull a DC barrel for you to look at it. So if you search for DC barrel, and let's also bring up an Arduino board. Arduino Uno. If anyone wants to dash me a supercomputer, I will gladly receive it. My machine is really suffering. Okay, so if you take a look at Arduino Uno, okay, so let's take a look at this. Okay. So this connector here, this is IOC, this connector here, that is what we refer to as a DC barrel. Okay? So that's the connector we have put in our schematic. So it's just a place we can connect a DC source, a DC power source. Okay. The one who asked the question, please, are you okay with it? Oh, okay, good. So if you okay, all right. So welcome back. So the connection, the DC barrel has three pins, okay, and how to connect them is what I've done here. Now, if you are using any other circuit designer, then you have to check the pin mappings for your circuit, the circuit designer, because it might not be the same as what we have in KiCad. Is that okay? So please take note of that. Please mute your. Thank you. All right. So this is going to take the input voltage. So let's say if we connect it to a 9-volt battery, it's going to take the 9-volt battery and produce a 5-volt out of it. Now the next thing we have to do is to convert part of this 5 volts to 3.3 volts using this voltage regulator. This is also a linear voltage regulator. So what we do here is feed in. What we do is feed it with the 5 volts input. Now, there is no need feeding it with a 9 volts input on the VCC. Okay, because if you do that, you're going to put so much stress on that. You're going to put so much stress on it, and it's not something you have to do. Okay. Now, linear regulators tend not to be very efficient. Okay, they tend not to be very efficient. So, for instance, for the 5 volts, if I power it with, let's say, a 9 volts power supply, then that means efficiency is going to be 5 volt output divided by a 12 volt input, right? Times 100. Can somebody do that calculation and tell us what percentage you get? 5 divided by 12 times 100. What do you get from that? Yeah, I'm still waiting. Can somebody do that computation? 5 divided by 12 times 100.
1.66.
Exactly. So you see, the higher the voltage you use for these linear regulators, the more inefficient they become. So what will happen is that you see your Arduino board heating up. Is that okay? So ideally, I recommend 9 volt tops. Now, do 5 divided by 9 times 100. Yes, what are you getting for that? 5 divided by 9 times 100.
It's 5.5%.
Exactly. So if you even use a 9 volt battery as your VCC, that is how inefficient your 5 volt regulator is going to be. So just imagine if you put your VCC directly on your 3 volt regulator, right? Then you are going to have, if you are using a 9 volt supply, you are going to have 3 divided by 12, right? Which is like a quarter times 100, which is 25% efficient. Okay, so you just don't do that. Okay, you just don't do that. So it's easy when you tap the 5 volts as the input to the 3 volt supply and produce the 3V3. So by doing this, we have 3V3 over 5 volt times 100. What do we get for that? For those who don't get what we are doing, we are just calculating the efficiency of the power conversion. Okay. Yeah, so 3.3 divided by 5 times 100, what does that give us? 66%, which is better than that using the VCC. So that's why we do some of this. Now, take note that anytime you are designing a circuit, make sure everything you are doing has a purpose. Okay, don't just.
Please, can you hear my time?
Can you come again?
Please, we use a resistor to break down the current.
Okay.
The regulation.
Okay. So when you use the resistor, we will actually talk about that later. We call it voltage division. Yes, you can divide the voltage, all right, but you have issues with current. Okay, so we don't use resistors to do this. Okay, especially for things like Arduino, you don't want that. You want your output voltage to be constant. Okay, but when you use a resistor divider, as the current demand changes, the voltage is going to change, and you don't want that situation. Okay, so you don't use resistors for this. But yes, you can use resistors to divide voltage. That's actually what they are primarily used for. Okay. All right. Thank you. Okay, so now we have our voltage regulators, everything set. We have a few minutes to end this particular session. And I think we're actually in time doing everything accordingly. Okay, but this is yeah, question, yes.
About the voltage regulation circuit.
Okay.
So advise someone to use a Zener diode or you always use the IT.
Zener diodes are not cut for these applications. Okay, you see, the fact is, if you use a Zener diode, you end up wasting a Zener diode way of dealing with voltage regulation is wasting it. Okay, it pipes excess current so that it goes away. That basically that's how a Zener diode works, and you don't want to be doing that. Okay, so for this application, and you see, we will be drawing a lot of current from this. Okay, so voltage regulators are the best way to go for this work. Okay, I like how active you guys are. Yes, I like how active you guys. Please, the senior members too, if you have anything to add up, please just draw my attention. Okay, thank you very much. All right, so we are done setting up the voltage for our work, right? But it is not very ideal in this state. Okay, why? Let's say we are using a battery. A battery actually has some latency. If I talk about latency, the time it will take to request for energy and the time it will take to supply that energy. Now, usually for most circuits that we do with in our everyday life, they are low frequency circuits. So energy demand, the speed at which this request go is nothing, right? Okay. There are also times where you can have noise. Okay, when we talk of noise, take it as some ripples, unwanted ripples on your incoming voltage. Okay, let's say you are using a very long cable to conduct the power. Your battery is somewhere and you are using a cable to connect it to Arduino. The cable alone could pick noise on while on the way coming. Okay, which will introduce some spikes on your signal. Okay, and this is something that you don't want. You want your sources to be as smooth and steady as possible. Is that okay? So what we would do here is to get another means of backing up our storage. Is that okay? So we are going to create some temporary storage systems that are faster than batteries in terms of supplying energy. Okay, now these backup storage components, we call them capacitors. So since they've come up, let us quickly look at what they are and what they do. Now, while setting up for the next PowerPoint, please, if you have any questions, you can ask. We will have our break soon, so don't worry. This is a crazy lecture, so yeah. I'm bringing up the next PowerPoint to talk a little or briefly about capacitors. So if you have any questions, please bring it up.
The AMS that we use,
Yeah.
is it not like an IC like when you have L7805? Don't we have some like L7803?
Actually, we have LM7803. We have the zero. I think it's not LM7803, but there is an IC like that for 3V3. But usually I use this AMS. Okay, we call them linear something LDOs. Linear. I've forgotten the D and the O. So if you remember, it just remind me. Okay. Yeah. So
There's an advantage.
yeah, one thing based that is that technically I researched so much into that. But what I know is that this LD AMS has a very low forward voltage drop. Okay, like it takes just a small amount. The typical LM7805 could probably draw about 2 to 2.5 volts to get to work, right? Which is actually a lot, right? So if you are dealing with very low power sources, that you need something that doesn't take so much, that doesn't drop so much. So the AMS, I find them to draw quite what do you call it? Their forward voltage drops is not so much compared to the LM70. You can check their data sheet for their forward voltage drops. Okay, I know these guys have a very low voltage drops. As in, they take just a little amount of your input voltage to work on themselves. Let me put it like that. Okay, yeah. Somebody also wanted to ask a question. Still bringing up my PowerPoint. Okay, please go ahead.
Let's say with this, we are not using a DC barrel, and then we are using AC. So that would mean that we have to involve the use of transformer to step in.
Exactly.
If we are stepping down this voltage, so let's say the transformer is taking like is stepping down the voltage to about 6 volts, and
Mm-hmm.
then at the DC voltage output, you want to be getting like let's say 3 volts. So that would mean that you will require the use of a voltage regulator.
Exactly. So
So I want to find out is that the voltage coming out from the AC to the voltage regulator that is necessarily need to be higher than that of the voltage that is being regulated.
okay, so if you take let's take the LM7805 for instance, right? Whatever input voltage, so any voltage from 7 volts to let's say 35, it is going to give you a constant 5 volts. That's what we need, and that's the reason we are using them. Okay. Now, usually when you do rectification, let's say like you mentioned AC, then I rectify it, and you still want to ensure that your voltage is constant. Is that okay? That's why in many applications you see people putting Zener diodes. So in this case, the Zener is serving as a voltage regulator. But in this case, I really want a stabilized output. That's why I'm using the ICs. The ICs do better compared to the Zener diode. Okay, so the ICs that we are using promises a constant 5 volt output, or if it is the 3V3, it promises a constant 3V3 output. Okay, and we can always trust that. Okay, yes.
So how about the ICs that are more or less like potentiometers that their voltages can be regulated? Is it advisable to use those now?
So remember when I started, so for instance, if you are using a switch mode power supply like LM, I think 2596, there is an adjustable version for it, or what you call the back converter. Some of them are designed to be flexible so that you can actually adjust a preset trimmer on it so that you could set it to the voltage you want. Okay. Now, the whole thing is that so far as you can trust that if you set the voltage, it is going to remain there. You are good. Is that okay? But there are most of them, they are not properly designed. So the more current you draw from them, you see that the voltage starts dropping. Is that okay? So for simple things like this, I would just advise use a fixed output voltage regulator. Okay, that even saves you component. If you are using this, you don't have to buy any potentiometer or other components to adjust your output. Okay, just besides, Arduino only needs the 5 volts to work, so there is no point using an adjustable voltage here. You get it? Unless you want it for some other reason. Please, is it okay?
Yes,
All right. Thank you. You're welcome. Please. Yes, yes, yes. Hey, we have 40 minutes to end this session. I have to talk about capacitors, so let's be snappy, okay? The next session is going to be more interesting in that order. Yeah, your question, please. Yeah, Koyo, I'm listening. Come again. I didn't get you quite well.
It's okay. Please, if the regulation circuit drains the 5 volts from the let's say 9 volts, where would the remaining 4 volts go?
Exactly. Good question. So the way these linear regulators deal with the excess voltage, okay, is by converting it to heat and giving it out. That's why they always warm up. Okay, so they convert it to heat. Are you okay?
It's okay, please. Thank you.
Yeah, so that means that if you operate it by saying that if don't connect like 12 volts to it, it means that if you connect 12 volts, you see it has to deal with an excess of 7 volts. That means more energy to dissipate as heat, and you don't want that to happen. Is that okay? So ideally, when you are powering an Arduino with an external voltage, I recommend 9 volts, because even at 9 volts, your regulator will be working at just 55% efficiency, which is still not good anyways. Okay. Yeah. Any other question before I start talking about capacitors? So remember, the reason I'm going to talk about capacitors because we said that the battery is not that fast in terms of discharging the energy that we need. And you see, we are working with a microcontroller. It works at a very fast frequency or speed. So we need to be able to supply it with the energy it requires exactly when it needs it. Is that okay? And also sometimes we can have noise and ripples adding up to our power source. It could be picked by the cables that you are using to link them. Okay, and we want to eliminate all these things, right? And the way we can do that is to use capacitors. Now, generally speaking, capacitors are like mini batteries. Okay, they work just like batteries, but then they have certain advantages that makes them preferable in some sense compared to batteries. Okay, so let's quickly look at capacitors. So generally speaking, I'm not going to go into the details and nitty-gritties of a capacitor, what it is and all that. Just what you need to be able to follow through this tutorial, and also a general idea so that you can use them properly. Okay, so the capacitors are just energy storage devices. First, like batteries, they store energy. Is that okay? And the difference between them and batteries is the energy density. That is how much of this energy they can hold. Okay. Now, most of the capacitors that we'll be using can hold just a little amount of energy, but that a little amount of energy is mostly all we need to. Oh, I'm actually not doing the presentation. Sorry. I started the presentation, but I wasn't presenting it. Okay. So mostly the amount that it will contain is all we need for our application. Is that okay? Now, there are, however, some special type of capacitors that we call supercapacitors. They can really hold so much amount of power. Okay, and we use supercapacitors for applications when or where current is supposed to be delivered at a very fast rate and in a large quantity. Okay, the chemistry of batteries actually puts some restrictions on how fast they can usually discharge the energy that we want. So that's when supercapacitors actually come in. So you can actually check them out in your free time to read more. They're actually fun to deal with. And these guys can actually hold so much energy. So if you put a couple of them together, you can actually use them as batteries. Okay, so the advantage of capacitors over batteries is that the capacitors can actually charge up faster and also discharge faster. Okay, a typical battery would take, for instance, when you are charging your phone, you know how much time you have to put in there, right? But a capacitor could just charge in a matter of a second. But of course, not to the energy density of the batteries. Okay, so just to clarify. Okay, so capacitors are usually ideal or used as energy storage devices when there is a faster energy demand or faster rate of energy demand. Now, in circuits, capacitors are represented by these symbols. Now, there are two types. Capacitors may be polarized or non-polarized. When I think I've already explained the concept of polarization or polarity, sorry. Whenever something, a component has a special pin dedicated to positive power and another dedicated to negative power, we say that it is polarized. Okay, in that situation, you cannot just connect that component anyhow. You can destroy it. You always have to make sure that the positive side connects to the positive terminal and the negative side connects to the negative terminal. Okay, so for non-polarized capacitors, This is the international symbol. Remember, I said that there are two schools. We have the Northern American style and the international or Europe and Asian style. Okay, so this is the international style, also used mainly by Europe and Asia, and this is the Northern American style. Feel free to use whatever style you want. I usually prefer using the international style. Now, however, let me also mention that some companies actually have standards in all these things. So they have standard in what kind of symbols to be using and all that. Okay, so in case you get the opportunity to work with a company, mostly they have these things defined. Okay, so the capacitors that are polarized, usually you see a plus sign on their circuit symbols. Okay, so take note of that. Anytime you see a plus sign, know that you are dealing with what? A polarized capacitor. If there is no plus sign, you are dealing with a non-polarized capacitor. This means that for these guys, I don't actually have to worry about how I connect them. I can connect any terminal to any pin. Okay. And in case you haven't seen a capacitor before, these are all examples of capacitors. We have fixed capacitors and adjustable capacitors, the same way we have adjustable resistors. Okay. Now, this here is a typical example of a supercapacitor, and you can see it can hold 3,000 farads. Trust me, you may not have any clue what this really means, but that is a lot of energy. Okay, that is a lot. A farad is 1 coulomb of current or charge over 1 volt. So having 3,000 farads at 2.7 volt, this is a lot of current. Okay, this is a lot of current. So this is an example of a super capacitor. Okay, now if you look at the nature of a capacitor, generally capacitors are made up of two plates. Is that okay? Two parallel plates with a space between them. These two plates are electrically isolated. Is that okay? That means they don't have contact. Okay. Now, sometimes you would have nothing in here but air. Other times too, you would have materials in between this plate. Now, these materials are insulators, and we usually refer to them as dielectrics. Is that okay? So anytime you hear a dielectric is basically an insulator, and as we know, insulators are poor conductors of what? Electricity. Is that okay? Now, depending on how the capacitor has been fabricated, most of them they have a coil of this flexible sheets of metal, okay, with their dielectric placed in between them. Okay. Now, what happens is that, for instance, when I connect this voltage, because the current cannot flow from this terminal to that, the charges build up on the surface of that particular the charges build up on the surface of the conductors, and when that happens, there is this thing called an electric field which generates between the two plates. Okay, now it is within this electric field that the capacitor stores its energy. So we say that capacitors store energy in their electric field. Now, I won't go into the details. I think I would have other sessions where I would take each component one after the other and do a detailed analysis of them, or a detailed tutorial of them. Okay. So for now, know that capacitors store charge in the form of what? Electric field. Okay. All right. So let's say I hook up this positive charge to this plate. It means that I'm going to have positive charges over here. Now, technically, okay, in electronics, when we talk of positive charges, we are only talking about the absence of electrons. And again, I won't do that lecture in here. If you are interested, check out my tutorial on Tech Foundation platform, YouTube platform. There is this lecture on Phatronics. Okay, check Phatronics. I think I explained these things. Okay, so anytime you hear of positive charges in electronics, it is not like we have protons or some positive electrons going on there. No, Positive charges simply refers to a state where there is an absence of electrons. Okay, so just put that in your mind. So we're going to have positive charges, roughly speaking, built on this plate, and negative charges built on this plate. And you see, the beauty of the whole thing is that if, let's say, we have 1,000 charges on this, positive charges here, we are going to have 1,000 negative charges here. Okay, so there is charges always conserved. Okay, so the energy that the capacitor stores, it's inside its what field. Now, a capacitor has a property that we call capacitance. Okay, and capacitance simply refers to the ability for a component to store electric energy. So that is where it gets its name from, capacitor, because it has what? Capacitance. Now, in English, when we talk of capacity, we are usually looking at a space where something can be contained, right? So the same way, capacitors, they have the ability to store electric energy in the form of what? An electric field. Okay. Now, capacitance is expressed as a ratio of the electric charge. Remember, we have, whenever electrons or charges move, we have current, right? So when the current is not moving, then the charges are not moving. We can't call them current. We can't call it current. We can only refer to it as charges, right? So because capacitors don't allow the current to move, it means that it will build up, the current will accumulate on the surface of the plate, and we can refer to them as what? Charges. So the way you calculate capacitance is by dividing the charge by the voltage between the plates. Okay, that is how you find out the charge of the capacitance of the capacitor. Now, capacitors are measured. Capacitance is measured in unit called farads, which is actually labeled after Michael Faraday, who actually is the father of all this kind of stuff. Okay, and when we talk of a farad refers to 1 coulomb over 1 volt. Okay, the value of 1 coulomb over 1 volt is what we refer to as a farad. Now, the energy that is stored in the field, you can always calculate it by using this formula. So the energy is 1/2 of the coulomb, the capacitance times the voltage. Okay. Now, I'm not going to go into details of these things. If you are interested, please just check them online. Okay. If I want to go into the physics of all this, a lot of us will get bored. It's interesting for me anyway, so I won't go there. Now that we know about what capacitors are, how do we use them in circuit? Okay, there are 2 ways we could usually use capacitors. One is by tying one of its terminal to ground. Okay, so we can always take a capacitor, tie one of its terminal to a voltage source and the other to ground. Now, when we do that, then the capacitor is being used to store small amount of energy. We are using it as a storage device. Okay. Now, there is also another way to use it by putting it between. So let's say I have a wire, I cut the wire into 2 and connect the capacitor in line with the wire. When you do that, then we are using it to block current. So in that case, you are not using it as a means of storing energy, but as a block for we will look at it. We call it coupling. Okay, we'll talk about it very, very soon. Okay, now let's continue. Now, whenever you want to use a capacitor in your circuit, there are certain important factors or parameters that you have to check. Is that okay? Very, very important. Now, the first thing is the voltage rating. Every capacitor has a voltage rating, and the voltage rating usually represents the total, the maximum voltage it can stand. Okay, so you always check the voltage rating. That means that, let's say right now for our Arduino, we are designing for a voltage of up to about 35 volts, right? We have to choose a capacitor whose voltage rating exceeds this 35 volt, else it can blow. Always remember that. So key thing, always check the voltage rating. The next thing is the tolerance. Capacitors have tolerance. Tolerance is like the percentage error that you can have. For instance, if a capacitor is rated, let's say 1000 microfarad, and has a tolerance of about 20%, it means that you may not have exactly the 1000 microfarad capacitance. Okay, you should allow a room for about 20% error. Okay, that's what the tolerance is. So always check this. Now there are certain applications where you need to meet like specific requirements. So in that case, checking up the tolerance is very important. Then the main reason we use the capacitors is because of their capacitance. Okay, how much of the storage or energy it can store, and all this, the value, how you choose these things depend primarily on what you are building or the circuit you are designing. Now, one important thing that comes in very handy when you are dealing with usually high frequency stuff is what we call the ESR, equivalent series resistance. You see, note that these capacitors are still fabricated or constructed with materials, right? And these materials have their inherent resistance. Okay, any material has an inherent resistance. Okay, so when you use these capacitors, to some point, this inherent resistance becomes parasitic, and depending on the application that you are using, you may have to consider this ESR when you are choosing your capacitor, because if it is too high, you can end up distorting your signals, and that may affect the performance of your circuit. So yes, equivalent series resistance is one of the important things to look at when you are checking, you are buying or selecting capacitors. Then another thing is their operating temperature. Okay, if you are doing applications for, let's say, automotive purposes, let's say you are designing circuitry to be used in electric vehicles, right? Now, these are situations where you are likely to be dealing with very high temperatures. Okay, so the capacitors you are choosing, you don't just choose them based on maybe their voltage rating or capacitance. You have to also make sure that the voltage they are rated for, or they are automotive grade. Okay, the voltage they are rated for can withstand the application you are using them to do. Okay, so the operating temperature. Okay, now there are different types of capacitors out there, and each of these capacitors have certain special characteristics. So in some cases, you will prefer one over the other. Okay, and it all depends on, again, what your circuit requires. Okay, now usually we have these types. We have electrolytic capacitors, mica capacitors, paper capacitors, film capacitors, non-polarized, and ceramic capacitors. Okay, I'm not going to talk about their details. You can check them online later. Okay, so these are all examples of capacitors. Some of our sponsors, I think Siratech, Novitel, Teskin, they are all component suppliers. Okay, so usually if you need help choosing some of these components, you can give them a call, and I know they will be able to assist you. Is that okay? But then all these things you see here are types of capacitors out there. And again, you choose these things based on the application you are designing for. Okay, so I'll share this slide with you for you to look at it later. Okay, now, like I said, there are two ways you can connect capacitors. At least I know of two ways. So if there is any other way I don't know of, please just draw my attention to it when we have a time for discussion. Okay, so we could connect a capacitor as a decoupling capacitor. Now, when we talk about decoupling capacitor, that is when we are using it as a means of storing energy. Is that okay? So we have a DC power source here, and we connect the capacitor parallel to that DC source, okay, and also parallel to our load. So over here, it's like when current flows from here, it will first of all fill up this capacitor. When this capacitor becomes fully filled, that is when the current will now go to the load. Is that okay? This is done so that in case this load requires current or energy so fast that this battery is delaying, the capacitor can discharge its energy for the load and refill itself later. Okay, so that is basically what the capacitor is doing when we use it for decoupling. Now, we can also use it for coupling. Now, usually you see this in amplifiers, okay, and when you are dealing with analog signal. There are times where, let's say you have a transistor, you have biased it in DC operating points, whatever. You don't want the signal coming to interfere with the other side of the circuit. What you can do is put a capacitor in between. Now, what will happen is that because the DC cannot go through the capacitor, it will be blocked, and there will be some form of isolation between the two sides of the circuitry. Okay, so whenever you use a capacitor in line, okay, so take note how it has been connected. It has been connected in line. When you use a capacitor this way, we say that it is acting as a coupling capacitor. So decoupling and coupling are just adjectives that describes how the capacitor is being used. But take note that whenever you want to use the capacitor as a storage device, then you need to connect it as what? A decoupling capacitor. Okay. Now, naturally, the reason capacitors are able to, we are also able to use capacitors to filter out some unwanted voltages, right? How is that possible? Capacitors naturally opposes the change of voltage. Now, you see, this thing is a simple thing to understand. Look here. When this guy demands a lot of current, energy from this power source, right? Technically, when this starts to deliver, there is going to be a small amount of drop in the voltage, okay? But then this capacitor quickly kicks in and fill up that chain. That means, so far as the capacitor is there, if the voltage tries to drop, it is going to release energy to counter that activity. That's why we say that capacitors, they prevent change, they oppose changes in voltage, because anytime the voltage tries to change, they come in and handle it. Okay, let's take it that way for now. Okay, so when you have a capacitor, when you have a capacitor as when you have a decoupling capacitor in a circuit like that, when I switch this on, if this capacitor is very huge, right? Let's say we are talking about 4,700 microfarad, right? When this happens, you will see that when you switch this circuit on, if this is, let's say, a bulb, it will not turn on immediately, okay? What will happen is that it will take some time, however small, for this bulb to turn on. Why? This is because when you turn it on, the current that rushes into the circuit, first of all, goes to fill up the capacitor. Okay, so only a transient amount gets to the load, and since it is not up to what could power or energize our load, the load will still remain up. However, because the capacitor actually charges up faster, it's easy. It takes no amount of time for the capacitor to charge up, and then now the current can now flow to our load. Is that okay? So anytime you have capacitors in circuit, that is the behavior that you see. When you switch your circuit on, you see that it takes time for the circuit to turn on. And similarly, when you switch the circuit off, for instance, if I take off this power supply, remember, this capacitor has stored energy. So the energy in the capacitor now begins to power up the bulb. So there are some devices, when you disconnect their energy, you realize that if there is this LED light on them, the light remains on for some time before turning off. Yes, it is because there is a decoupling capacitor in there that is discharging its energy through that LED. Okay, so it takes time for it to go off. Okay, so I think, yep, that is enough about capacitors. Now that we understand this, if you have any question in the next 3 minutes, we have 50 minutes to end the session. In the next 3 minutes, if you have any questions, please feel free to ask before we go back to our schematic to place capacitors. Okay. Come again. I didn't hear you well. Come again. If capacitor already have current, no, that's not what I said. So the capacitor will only have current, will only build up charges when you connect them in a circuit, okay? Apart from that, when they are just there, they don't have any charges in them. I don't know if that makes your... Okay. Please, if you have any question, we're going to the last part of this session, which will be placing capacitors on our... Yeah, so if you have any question, yes, sir. Okay.
Okay. My question is for the charging and then the discharging of that of the capacitor.
Yeah.
Let me try a bit the theory. Well, we have a time constant, and that's the RC.
Yeah.
So I want to ask, when in the circuit that you showed us, that's from the DC store, the capacitor and the load.
Yeah.
So must there be a resistor connected in series to that of the capacitor so that it will determine the time that it's charging for the discharge?
Okay.
So you can just do it like that.
All right. Thank you. Now, when you combine a capacitor and a resistor, you are forming something called an RC filter. Okay. And usually we do this when we want to deliberately create delays in circuits. Okay, so yes, you talked about the RC constant, which if you choose the right amount of resistance and capacitance, you can actually build timing into your circuit. But in this case, we don't actually need that. Okay, we in fact need the capacitor to charge up and discharge as fast as possible. However, if there is a situation where we want to regulate how long the capacitor should charge and discharge, then yes, we can introduce the right value of a resistor. Okay, but in this case, that is not what we are trying to achieve. So we don't need the RC parameter over here. Okay, I don't know if you're okay with that. Yes. All right. Somebody.
Please, I do have a question.
Okay.
My question is, looking at the computer, I'm using LM35 as the temperature sensor.
Okay.
But then I face this challenge where if I'm trying to take the signal from the LM35, it keeps fluctuating. At some point, when the temperature is increasing, the reading from the LM35 further decreases. So I said about this, and they were like, it's as a result of noise coming from the LM35. So in cases like this, am I going to use the voltage divider, or I'm going to use either the coupling or the decoupling of capacitors to make that work?
Okay. Thank you very much. So I would have been happy to answer this question if I probably saw your circuit right now. But now I'm going to do a gentleman gets here. First of all, when you are using those sensors, right, they are very sensitive. You are dealing with analog signals. So that means they are not immune to noise, right? So what you do is you could probably put a decoupling capacitor on the power source of the IC. So if it is LM35, the power pin, the 5-volt pin, you could put a decoupling capacitor very close to it. Okay, that will stabilize the input power. Now, once you do that, the next thing is to make sure that the signal, where if you are using a PCB, where you have routed the output, is not going through any high frequency digital signals or whatever. Okay, just that. Don't worry. We will, in the course of this, I will talk about those things when we get to the PCB side of the whole thing. Probably it will help you answer your question well. Okay.
Okay, thank you very much.
Yeah, right. Please, any other question? We have just 10 minutes to finish this side.
I also want to know if this session is being
recorded. Yes, it's being recorded. I'm only hoping the sound from you guys is being recorded. So I can only check when I'm done. But it's recorded, okay? It's recorded. All right. So quickly, we have just 10 minutes. Let us place our capacitors. Then, if we have more time, I'll take some more questions, okay? So, switching the view to keycard. Switching the view to keycard. Okay. I need a studio for these things. Seriously. All right. So, this is what we're going to do. first of all, I'm going to put one capacitor on this DC barrel. Now, this capacitor is going to serve as a filter. I'm going to use it to filter out any noise that might come with the DC voltage as it's being input. Okay, so let me adjust this a bit. You can always press G to drag any component. Okay, and then also adjust this a bit. I'm going to put a capacitor here. Now, I usually do this just for dealing with high frequencies noise that may come with my power source. So anytime I put a connector, I put this small value capacitor there. Okay. Now, we already know how a capacitor symbol looks like. And this time, the capacitor I want should be, okay, so let's see, our voltage could go as high as 35 volts. That means that the capacitor I'm using should have a voltage of, usually my rule of thumb is to pick twice that, or at least 2/3 of the required. Okay, so I'm going to use a 50 volt capacitor, a capacitor with a voltage of 50 volt, so that even if my input voltage is 35 volt, I still don't have to worry about that. Okay, so, and I also need a normal ceramic non-polarized capacitor to set for that. So set for C underscore. So C is the symbol for capacitors, right? But I want a smaller version of it. Oh, my PC. My memory is really taking the hits. Okay, so C underscore small, okay, to give me the smaller version of the design. I'm going to put it here, and here is going to function as a decoupling capacitor. Okay, so I'll press V to set the value, and this one usually I use a 1 nanofarad capacitor, something very small, so that it can deal with high frequency noise that comes with. Okay, so move this about to organize it. Okay, and also reposition. So I'm using a combination of hotkeys in keycard, M to move, R to rotate, and what do you call it? Control for fine adjustment. Okay, so now connected over there and then over there. So you see, I've connected the capacitor parallel to my power source. So it is serving as a decoupling capacitor. Now, when we start routing, I'm also going to talk about how you place these decoupling capacitors in your circuit. Now, we actually also need a main capacitor bank that is going to serve as a temporal storage for, or a buffer, a temporal buffer for our VCC, our power output. Okay. Now I'm going to, on the Arduino, I see two of them, and they are rated 47 UF, 25 volts each. So I'm going to use the same capacitance, and this time around they have to be polarized capacitors. So I'll go to place parts and pick C in keycard for polarized capacitors, C underscore polarized, and I want the small version. Now look at how it looks like, right? And if you select the US version too, you see how it looks like. Okay, and like I said, I prefer to use the all right, so I'll put it here. I need two of them actually, so let me click on this and set this to, now this one probably I will use 100 microfarads instead of the 37 by the Arduino board. And let me press Ctrl D to duplicate this. Probably this is taking too much space. Let me rearrange that. Okay. All right. Now, the next thing I'm going to do is to connect this to the VCC net. Okay, so this capacitor is going to serve as a boost capacitor for the VCC net. Now, take note, you may not physically see a wire connected here, right? But take note that anytime I connect the same port to something, it means internally they are connected. Is that okay? So for instance, this capacitor is connected to this point and is connected to that point. Is that okay? So take note of that. Okay, let me just delete this and bring, I'm going to use the same value for the 5 volts net. I'm going to use the same value for the 5 volts net. And then connect that. And again, here we are connecting this as a decoupling capacitor for the 5 volt net. But the main purpose here is to store have a temporal storage for energy, right? For all the 5 volts devices that will be pulling energy from the voltage regulator. All right, so as usual, let me put that here. I'm not going to put some of these caps on the 3 volt net. I'll put rather smaller values on the 3 volt net. Okay, so let me just grab something like this, but this I'm going to use a 10 microfarad ceramic capacitor on this. Okay, so that's going to be the capacitor on that. It's not electrolytic and it's actually okay for the reason I'm using it for. And you can see that in here I'm not using any capacitor because it already has a capacitor. Now ideally, I think the component manufacturers recommend, if I have, let's say, 100 UF here, I should have like 10 UF over here. Okay, just that this 10 UF I'm not using an electrolytic. It's okay. I haven't actually had any challenge with this before, but if anybody has gotten challenged doing something like this, please let me know. Okay, all right. So we're almost done, and our first session is also almost up. Okay, so I'll put in here, so this usually I call it smoothing caps, or let's just call it boost caps. Okay, and they are just serving us. So that means that anytime our IC, that is the Arduino microcontroller, would request for energy, the capacitors are going to discharge quickly to supply that energy, okay, before the battery refills it. Okay, so something like that. All right, so that brings us to the end of the very first session. You see, one thing I need you to pick is how the process goes. Okay, you see that I'm doing things intuitively. I'm following the whole idea. Okay, what do I need to do first, followed by what next, in that order. Is that okay? So in the next session, I think what we'll be doing, we'll be adding some resistors and other stuff. Okay, I'm telling you, the next session is even much interesting than the previous. So we break and have a 1 hour 30-minute break. Okay, so that means you'll be coming back at 1:30. Thank you. If you have any questions, I can take just 1 minute to take questions before we break. Yes, so if you have any questions, please. And also, let me say that if probably I'm moving too fast or you have any comment, just send it to me on WhatsApp. Okay, so I'll check them up and probably adjust. And anyone who can help me with the co-admin thing, please help me with that. Okay, thank you. All right, so any questions? You are breaking for the first part. Those who just joined, sorry, we'll be breaking very soon, but I'll be uploading the video right after. So if in case you missed it, please check it. Okay, check the video. Any questions? Yes. Joel, your hand is still up, or it was the previous step. Joel, is your hands up, or? Very soon, right? In fact, yes, I will share. If you're on the platform, then don't worry. The moment I upload, I'll share the link. Okay, so if you are not yet on the platform, please. You are trying to. Please come again. You say you are trying to do what?
No, what I'm saying is that you said you share on the platform, so I said okay. That's okay.
Oh, okay, okay, all right. Okay, thank you very much for joining. This is crazy, I mean, but it's good to still know that a lot of people are still online. I hope I'm able to meet your need. All right. So thank you. We reconvene here in 1 hour 30 minutes time. Yeah, yeah. Could you please check your mic? I didn't get you. Hello. Was somebody asking a question?
So, since we're talking about a platform, is there a WhatsApp platform?
Yes, a WhatsApp platform. If you've seen any of our ad, the WhatsApp and Telegram platform are all in there. Okay. Please, if you have any questions, get them written down so that when we start the next session, you can ask before we proceed. Okay. I'm here for you, so make sure you understand before we continue. Yeah. Yeah. So in 1 hour 30 minutes time, so that should be 1:30 GMT. 13:30 GMT, yes.
Mr. Bean, Mr. Bean,
Yeah.
can you please go back to your schematic?
Whoa, okay. Okay, sure. Yeah.
Yeah, and please, the PowerPoint.
Okay.
Can you please brief me please again how you do the PowerPoint?
How I got it.
Yeah, the PowerPoint.
So you want me to show you how to select the PowerPoint? Is that what you're asking?
Yes, yes, yes.
Okay, so we go to add components and then you search for DC barrel. It's called a DC barrel. So DC barrel. Sorry. DC barrel. Okay. So there are various types, but you make sure the one you are selecting has 3 pins, and that's the pin.
Mr. Bean,
Yeah,
Mr. Bean,
yeah. Just call me Prof,
I
okay?
wasn't referring to that.
Uh-huh.
I wasn't referring to that.
Oh, okay.
I was referring to the one in the PowerPoint.
Oh, okay. Yeah. Sorry. So here you go to add PowerPoint, okay? Then you type in the signal, the ports you want. So if you want VCC, VDD, you just pick it here and place it, okay? But then in KiCad, to avoid a certain DRC errors, you have to also put these flags on them to tell KiCad that hey, these are not you don't as these are like single point connectors or something like that. So don't flag any DRC stuff, right? Don't worry. Probably when we come back out, I can take you to it again. But I don't know if you're okay. All right.
Prof,
Yes, sir.
Prof,
Yes, sir.
the KiCad, which version is this one?
I'm using
KiCad
version
is the
6. Version 6.
6,
Yes.
Alright.
Okay. So I'm going to snap this and post it on the page so that if you are following along, you could probably take time to do it. Okay. All right. So thank you all. See you in the next. 1 hour 30 minutes. Yes. Okay. One more question.
Please, I wanted to know that is all the 3 power connected in series, or like I can see that we have this DC barrel, the 5-volt regulation, the 3-volt regulation, the boost capacitor. I wanted to know that if they are all connected in series.
Okay, so simply how to look at it is this. Okay, anytime you see VCC somewhere, it means that those points are connected together. So for instance, if I highlight this VCC, you see that all other things that have VCC have also highlighted, right? It means that those points have been connected together. So it's not necessarily a series or a parallel kind of thing. Just know that those nets are connected to each other. So it's like I have a wire and I have twisted them together like that. They are connected together. Okay. So the same way, if you pick this 5 votes, you see that every place with 5 votes has been highlighted. So it means that they will be physically connected together. All right. I think we have to go. Please, if you have any other question, write it down. When we start the next session, then you ask it. Okay. Thank you.